What specific limitations of existing reasoning methods does adaptive parallel reasoning, APR, address, and why are these limitations significant for language model performance?
Adaptive parallel reasoning, APR, addresses several significant limitations of existing reasoning methods, particularly those related to serialized chain of thought and fixed parallelization structures. First, serialized methods produce lengthy output sequences that increase latency and strain context window limits, making it difficult for models to attend to relevant information effectively. Second, parallel methods like self-consistency lack coordination between inference paths, leading to redundant computations and suboptimal resource utilization. APR overcomes these issues by allowing language models to adaptively distribute inference time computation through a parent-child threading mechanism, enabling efficient exploration of the solution space without predefined structures. This flexibility not only enhances performance within fixed context size constraints, but also improves scaling behavior and reduces latency, ultimately leading to better overall task success rates.
How does the adaptive parallel reasoning method work? Please illustrate the process step by step, including the roles of parent and child threads during inference.
Adaptive parallel reasoning, APR, operates through a structured process involving parent and child threads during inference. Initially, the parent thread begins decoding and can invoke a spawn operation to create multiple child threads, each tasked with exploring distinct reasoning paths in parallel. These child threads operate independently, utilizing the context provided by the parent thread, and they execute their inference tasks simultaneously. Upon completion, each child thread returns its results to the parent thread via a join operation, where only successful outcomes are communicated back, allowing the parent to continue its decoding based on this refined information. This hierarchical threading mechanism enables APR to efficiently manage inference, reducing latency and optimizing the use of the context window by limiting the information passed back to only what is necessary for the parent thread's decision-making.
Can you provide a simple example that details the inner workings of the APR algorithm, including how parent and child threads interact and how information is communicated between them?
The adaptive parallel reasoning APR algorithm operates through a hierarchical structure of parent and child threads, facilitating efficient reasoning. For instance, during the countdown task, the parent thread initiates a spawn operation to create multiple child threads, each tasked with exploring different reasoning paths based on distinct contexts provided by the parent. As these child threads execute their inference in parallel, they independently search for valid solutions. Upon completion, each child thread uses the join operation to return only the successful solution paths back to the parent thread, discarding any intermediate traces from failed searches. This targeted communication allows the parent thread to continue its reasoning process based solely on the concise and relevant information received from the child threads, thereby optimizing the overall computational efficiency and minimizing token usage.
What are the theoretical benefits of using adaptive parallel reasoning over traditional serialized methods, specifically in terms of efficiency and performance within a fixed context window?
Adaptive parallel reasoning, APR, offers significant theoretical benefits over traditional serialized methods by enhancing both efficiency and performance within a fixed context window. Firstly, APR allows for more effective search and reasoning within the same context size constraints, achieving a success rate of 83.4% compared to 60.0% for serialized methods at a 4K context window. Secondly, it exhibits superior scaling behavior, demonstrating better performance improvements, 81% versus 66.6% when the total compute budget is increased to 20K tokens, thanks to its ability to parallelize reasoning across multiple child threads. Additionally, APR maintains improved performance at the same latency, achieving a success rate of 75.2% compared to 57.3% for serialized methods at around 5,000 milliseconds. This efficiency is further underscored by APR's ability to minimize token usage in the parent thread by discarding intermediate traces, thus optimizing the overall computational cost of inference. Overall, APR's adaptive allocation of inference time compute resources allows for a more efficient exploration of complex reasoning problems within constrained context limits.
How was the effectiveness of adaptive parallel reasoning validated in the experiments, and what specific metrics were used to measure improvement over baseline methods?
The effectiveness of adaptive parallel reasoning, APR, was validated through experiments on the countdown task, where it was compared against baseline methods, specifically the serialized chain of thought reasoning, SOS+, and self-consistency selection, CONSA-10. The evaluation metrics used to measure improvement included accuracy, which was defined as the percentage of countdown problems successfully solved, and computational efficiency, assessed by the total tokens generated during reasoning. Additionally, latency was measured using sequential tokens and real-world latency, which reflects the wall clock time required to solve a task. Results indicated that APR achieved higher accuracy, 75.2% versus 57.3% at around 5,000 milliseconds latency, and better performance within the same context window, demonstrating superior scaling behavior and efficiency compared to the baseline methods. Overall, APR's ability to adaptively allocate inference time compute resources led to significant improvements in both performance and efficiency metrics.
What are some of the identified limitations or drawbacks of the adaptive parallel reasoning approach? How might these limitations affect its application in real-world scenarios?
The adaptive parallel reasoning (APR) approach has some identified limitations, particularly in low compute regimes where it initially underperforms due to parallelism overhead, as some tokens are used for orchestrating threads rather than directly contributing to the search. This can lead to inefficiencies when the compute budget is limited, potentially hindering its effectiveness in scenarios where quick responses are critical. Additionally, while APR improves performance by allowing for broader searches, it may still face challenges in maintaining coordination among child threads, which could result in suboptimal resource utilization if not managed effectively. Furthermore, the reliance on reinforcement learning for optimizing the model introduces complexity, as it requires extensive training data and computational resources, which may not be feasible in all real-world applications. These limitations could restrict APR's applicability in environments where rapid, efficient decision-making is essential, such as in real-time systems or applications with stringent resource constraints.